It's always a pleasure to come back to IPAM. I've been to many meetings here. First one on machine learning, though. It's a bit intimidating. So I will be discussing a little bit of trainability and accuracy of artificial neural network and try to present some viewpoint that we have pushed forward and several groups have contributed to. And the big issue is to try to understand from a mathematical perspective or applied mathematical perspective some of the amazing success that we have seen emerging with the machine learning. And in particular, and this is not an audience where I need to discuss that at great length, but as Remy was saying in the previous slides, there is something which is quite remarkable about the fact that it used to be the case. Some of the workshop I came here were only discussing about curse of dimensionality and the fact that this would never be broken, that it would be impossible to represent things in high dimension, so you had to do Monte Carlo or things like that. And then machine learning came about, and all of these things starts to happen, which is pretty high dimensional representation of function if you think about it. And so there is this issue which Remy was saying, which is that, well, is this working because image or speech recognition or even cognitive tasks are actually inherently low dimensional? Or is it that neural network can actually accurately represent high dimensional function? And of course the answer will be a bit in between, which is that high dimensional function that have some features that are inherently low dimensional can be represented even though one might not be able without the machine to detect them. Okay? And being an applied mathematician, I want to look at that from the viewpoint of whether this can actually alleviate the curse of dimensionality and provide new ways to do scientific computing, which is likely to be the case. There will be many talks this week about that. Okay, so this slides is mainly to fix notation because most of you know this already, but so that we are kind of all on the same page. So what I'm going to be discussing is how to use a neural network to represent a target function that's given to me. Okay, so this target function has a domain which is embedded in RD. D is typically fairly large, and that's the kind of application we would like to look into. And it's a scalar evaluate, and so the neural network representation is simply a superposition of units in which the units takes the input plus a parameter, which I will call x and z, and then there's a weight, and then you weight all of these units, and that's the approximation that you would like, by which you would like to represent the function. Just to fix notation, there I will use indiscernible these two things. So c phi at the x of z is the same as this phi of theta. It's just to kind of be a little bit more compact. And the parameter to be fit in the representation enter, for example, if you use a ReLU, which is quite standard, in the following way, which is this, that should be the phi hat. It's just the rectified linear that you all know. Okay, so these parameters, how do you fit them? Well, you measure the approximation via a loss function. So what is the loss function? Well, is the L2 norm of the discrepancy between the representation and the target. Okay, and where you take it weighted by a certain measure, which is your data. So you can think about this as being the expectation with respect to data. That's what you embed of the square discrepancy between f and fn. Now, of course, in practice, you don't have access to all of the data, so you cannot perform this integral analytically. And so what is done is that instead of using the exact loss, you use the empirical loss. What is the empirical loss? It's just you do an average over some data that are drawn from the data set nu, and that's what you call the batch, and there is P of them. Okay? And then the final kind of element, ingredient in this training is the training itself. What you do is that you train the network by adjusting the parameters using stochastic gradient descent. So what is stochastic gradient descent? It's just gradient descent on the empirical loss. Okay? And you do that with a training rate. So what you do is you compute the gradient of the loss, and then you take steps in the direction of C plus descent until this algorithm converge. Okay? And of course, machine learning is a very, very fast field. This is really a caricature of what is actually done in real neural network, but it's a caricature that captures the main element, I would argue.
And this is one layer, right?
This is one layer, yes. You could, if you wish, you could pass this through a softmax, or you could have deep neural net, but in which the last layer is wide, in this way. At the end of the talk, for most of the talk I will be discussing this case. At the end of the talk I will tell you all these old pictures generalized for certain deep neural network. Okay? So if you have never seen a network, training itself, this is a planted neuron in a sphere. There are the two neurons that are there. The red dots are where you start the parameters and their weight. And then when you let them go, they all go and they find the planted solution. And here you have the function representation that converges very quickly and the loss that goes down. Okay? This is low dimensional, so there's no surprises here. Now, what are the puzzle that you have? Well, I repeat here what the main building block. Well, the puzzle is that, if you look at the first one is that if you look at this loss function here, and you think about it as a function of these parameters, because the unit is nonlinear, this loss function here is typically non-convex. So you should expect that if there's a lot of parameters and dimension is high, that this landscape will be rugged. Certainly, it will have many local minima. And so it's not clear at all why the stochastic gradient algorithm that you use here would identify anything else than a local minimum where the loss is actually quite bad. Okay, so there's the question of, can you actually train this network? Or why are they trainable? Because we know that they are trainable. There's another question, which is directly relevant if you think about the curse of dimensionality, is that you could ask, well, even if I can train the network, I'd like to know how the representation error, meaning the loss, for example, scale with the size n or the architecture of the network. But in particular, right, you could ask if I increase n in this representation here, so I take more and more units, how will the error decreases as a power of n, which power? And then there's another question, which is the question about generalization error is how does it scale with the data size? Because at the end of the day, you'd like to represent this function well, not only on the data set that you have to train the network, but also outside of it. That's the whole point. And so the question is, how will that scale with p, which is the size of the batch? Okay? And just because I know that there are various notations that are being used, please take note that here n will be the number of units and p will be the size of the batch. Okay? Now, there's a little remark to be made here, right? Which is that what is done here is fairly different from what is done in standard numerical analysis. Because standard numerical analysis, what you would do when you do functional representation is essentially the basic of finite element or Galerkin is that you take a linear superposition of known basis function and you just need to adjust the weights. Okay? If you do that, if you use this representation instead of this one, then obviously what you get here is a quadratic functional in the C's, and so optimization is easy because you just need to solve a linear system, right? Now here, you have something which is nonlinear, so you have a non-convex optimization, which is hard, and so we believe that there might be a trade-off between, okay, the training might be more complicated, but maybe the representation error is better. All right. I forgot to mention, and that will be important in next slides, that I have weighted here these sums by a 1 over n. And there's a reason for that, which is the following. Okay, so that's what I just said before. And the reason is that there is a set of results that I'm going to be building upon, which are about the theoretical approximation power of a neural network. They are quite old. They come from the 70s and the 80s, and that are generally referred to these days as the universal approximation theorem, or UAT. They go back to Symmeco, Park, and Barron, etc., etc. And what they say is the following thing, and that's why it's important to have this 1 over n. They say that if the unit phi is discriminatory, essentially that means nonlinear. I can give you a precise definition later if you want. Then essentially, if you take any function in L2, you can approach it using the neural network if you had infinitely many units. So what does that mean? Well, that means that you can find, if you give yourself any target function, you can find a function which is such that you can represent it as a superposition against a radon measure of the units, which is such that this guy will be within epsilon of your target. Okay, that's one result. And then there's another one, which is kind of the continuation of that one, which is to say that it can also be realized with a finite number of units, because you can always think about this object here, so this expectation with respect to the random measure, as essentially the limit as n going to infinity of a weighted sum, where you take certain ways Cj and Zj, and what you simply need to do is that you need to draw them independently from a probability measure mu. That one is a probability measure, not a random measure, which is such that if you think about its first moment for every z, it gives you the gamma. Okay? So, the universal approximation theorem quantifies the theoretical approximation power of a neural network, essentially by saying it quantifies capacity to represent function in a given space. This space is something which is associated with the unit, and is a space of function, that is almost a tautology, it's a space of function that you can represent by superposing these units with any random measure that you can imagine on your space. Okay? And once you have that, you realize that it also gives you immediately a Monte Carlo error bound not only on the approximation error, but also on the generalization error, which scales like this. So let me go into that, maybe speak about this colloquially first, just in case, for non-expert, that's kind of ABC of probability, which is that if you look at any representation like this, and you assume that you draw the parameter from a distribution mu, okay, independently, well, as n goes to infinity, you have the two pillars of probability theory. The first one tells you, the law of large number tells you that this Fn will converge to this, in whichever sense you want this convergence to occur. And then there's central limit theorem that's essentially say, well, if I take that guy, I subtract his limit, I scale it by square root of n, I should get some Gaussian field. Okay, and so this is a bit sloppy, but that means essentially you can imagine that you have an Fn that goes like f plus some error, which is Gaussian, which scales like a square root of n. Right, and that's the standard Monte Carlo scaling that's appearing here, right? That's the same as saying that, well, put in the loss, that would give you the n minus 1. That beats the 1 over n to the, 1 over d, right, here, which is that there's a 1 over d. Otherwise, that would be too good, obviously, which is that the one that you get if you were to do Galerkin truncation, okay? So now going back to this, right, so that explains that, and I will go to this result later on. Right, it says that, if you want to phrase that more precisely, that universal approximation theorem gives you Monte Carlo error bound, where you can relate these constants here to the norm of the function in that space. And I'll explain to you why that's the case later on. Okay? So I'm building on something here which I didn't say already, which is that this space here is not an Hilbert space, it's a norm space. And so you can introduce a norm, and the norm is what? Is you can introduce the TV norm, the total variation norm of the target function here, which is simply you take the total variation of this random measure and you minimize it over all random measure, which gives you the target. And it turns out that this defines a norm. Okay? And so in principle, right, if you can relate C and C prime, this constant that appear in the approximation error and the generalization error, to the norm of the function here, which itself depends on the unit, that gives you in principle a way to quantify the quality or the accuracy of the unit and the approximation error that you have in the network. Okay? Now, why is all of this a little bit academic? Is that unfortunately what the universal approximation theorem doesn't tell you is how to get the gamma star. Right? It's an existence result. Okay? And so unless you find a practical way to identify what this random measure is, well, you're stuck. There is nothing here that you can use. But it's a kind of, it's a sanity check, which tells you that there is something to look for that in principle has good properties. Okay? So with this preliminary, let me explain a little bit what we're going to do. And this is joint work. I forgot to say that on the first slide. This is joint work with Johan Bruna, my colleague at Courant, Zhengdao Chen, a student who is sitting back in the audience, a student at Courant, and Grant Roskoff, who is a postdoc at Courant and starting a position in Stanford next year. Okay, so what we're going to do here is I'm going to explain what can be done if you do something a bit different from what I explained on the first slide in terms of training, but it's a minimal patch on what one would typically do, and there's a reason why we need to do that. So first of all, right, one needs to realize that learning this random measure directly is difficult. That's because if you remember the representation itself, it's given on terms of the C's and the Z's. And so what you typically can learn are these parameters, which give you an approximation of a measure mu star, right, which is a probability measure, which is such that its marginal over C's actually give you the gamma. So first of all, we're going to do that. I'm going to show you how we can think about optimizing mu star, of course, always keeping in mind that what we do in practice is only playing with the parameters. And then to guarantee conversions, I'm going to do something which is a little bit different. I'm going to lift. So if you think about this, is that you can lift the Radon measure into a probability measure. We're going to lift one more time, and I'm going to use probability measure in a space that's slightly bigger for a reason that I will explain in a minute, where you introduce, in addition to this C, which I will call charge, even though they are weight, you introduce an additional weight, this W, okay? And so what we're going to do with that is that, we're going to use the following, representation, which is the same as before, except that they've introduced these weights. Okay? And if you look at it like that, it seems that it's a little bit redundant because they have weights and other weights, but you will see that they play a role that is different in the optimization, and that will actually be quite important with what follows. And then that's one part of the ingredient. And then instead of using the empirical loss that I showed you before, which is just that one, E of nu p here is just expectation over the data set of size p, the empirical one. So instead of using this guy, right, with this representation, I will also add a term in the loss, which is a term that rigorizes things, and which is simply the sum over I of wi, the same way as over there, and then ci to the q, where q is any power that's bigger than 2. Okay? And the reason why we will see that later, the reason why we will need that is that this will guarantee that you can not only learn the network, but that you can keep the TV norm, or the TV of the measure, sufficiently low so that you can have a controller guaranteed on the approximation and generalization error that you have after training. I'll get to that in a minute. Okay? Okay, and so explicitly, if you just look at this, right, I have written it here in terms of f, but you can think about that simply by, you can expand everything and think about it in terms of the w and these f's. So this is like something like this, where the f and the k are just, so this is a constant that's irrelevant for the optimization. The f is just the expectation of the target multiplied by the unit, empirical expectation over the data, and the k, this kernel, this quadratic, the kernel, which is no, not quadratic, but linear, in theta, is just the expectation of the unit square, essentially. Okay. Now, once you have done that, what you do, well, I go back to simply gradient descent, and I'm gonna, for the purpose of the talk, I will simplify this a little bit, and instead of using the standard gradient descent, which in practice, of course, is to have a time step that's finite, I'll just consider its time continuous variant because it's simpler for analysis. Okay? And so what you write down is that you just write down the gradient descent dynamics of the parameters and these additional weight over the loss. But by adding a constraint, you remember that, and that's what will make the weights a little bit different, and I'll explain to you in a minute. You remember that I want to introduce the weight, and I want to guarantee that this guy, which is this lifted probability measure, itself projects into a probability measure at this level, okay? And the way to do that is actually quite simple, is you do gradient descent over the loss function with an additional constraint that says that you preserve the normalization of the weights. You don't allow them to kind of vanish to zero, which would otherwise would happen if you don't put a constraint. So if you do that, you can write down this gradient descent. They are here, right? G will be the Lagrange multiplier that enforces this constraint. And there's one more little thing that you do, is that you do it, and that's where the weights and the parameter will play a different role. You do it by using a different metric for the gradient descent in theta and in W. And the metric is this prefactor here. It is n divided by W or n alpha times W that you use, okay? So it's useful to think about it like that, but at the end of the day, the equation that you're writing are just the ones that are here. So this is exactly the same equation that you would have if you do standard gradient descent, except that f contains a rigorization term. You need to remember that. And there is a weight that has been included, but that's not very important. And then there's an additional dynamics for W, which is this one, with a Lagrange multiplier term, which can be computed explicitly and just guarantee that this constraint is always satisfied. Okay? So you use different metric for theta and W, and it's very easy to implement in practice. A simple patch on SGD. I mean, you can do that in TensorFlow or any of the packages. Okay, so that's one ingredient. Now, I want to connect this to the picture that I said before, which is that at the end of the day, I'm not that much interested into what the parameters or these weights do per se, because they evolve on something which is quite complicated. What I would really like to know is what the function representation associated with them do as I train the thetas and the w's. Okay? So there's a way to, think about that, which is in the following way, which is, well, that's a bit of a tautology, but if I can think, right, using the interchangeability of these parameters, that I will think about particles, because I'm going to rely on theory from particle system, interacting particle systems. If you think about them as particle, you can think about the Fn, which is just the sum over omega I, the phi at theta I, as being an expectation with respect to an empirical probability measure, which is this probability measure here. Okay? The reason why you can do that is because of the interchangeability. It doesn't matter which label you give to a W or a theta. They all play the same role in the network. So you can write down, instead of thinking about these guys, you can start thinking about this measure here. Okay? And if you know what this measure does, well, you know what this guy do, which in principle is what you would like to quantify and analyze. Okay? Well, there's another little part of the puzzle that you can write down immediately, which is that essentially, and this is chain rule, you can if the theta and the W satisfy these equations, you can write down an equation for this empirical measure. So I wrote it, it should really be written in a weak form. I just wrote it here as a PDE, but if you test it against something, it would give you what it is that you'd like to have. This equation is exact. It's just what, if you think about looking what this guy does, well, the evolution is given by this, where you have introduced this kernel here. So it's a nonlinear Liouville equation because the potential that you have here depends itself on the measure. Okay? And the mu n that is there is just the projection, the one that you're actually interested in, the one where you eliminate the weights. Right? So that's one thing. And now come, maybe this was a bit of a long detour to explain why we got all the weights. Now we can take this equation, and you realize that because of the way it has been written and derived, that's why we took this specific metric here, you can actually write down a closed equation for mu n. How do you do that? You multiply this equation by omega, and you just integrate. If you do that, these two terms are unaffected. This one you do by part. There's a W here. This kills the W that you multiply to. You use this form, and what do you obtain? You obtain this equation here for mu n. It satisfies what in the field is called an unbalanced transport equation, which is that this is the standard transport term that you would get in the nonlinear Liouville equation. And now you have added terms here that encompass the role that the weights are doing, and that in fact do non-local transport at this level. Okay? One of the problems, and I'll get to that in a minute, when you go into these frameworks, is that when you look at particle systems, even though it's a gradient flow, I'll get to that. Well, let me explain that in a minute. So if you look at this, you can think about this equation as essentially, so this guy here, this V, is the functional derivative of the quadratic energy, which is simply the loss viewed as a functional of mu. Okay? So if I rewrite the loss as a functional of mu, it's written like this. If I take its gradient with respect to mu, I get the V that I have written on the previous slide. And this V is used in the transport equation that way. So it's essentially what it says, in a nutshell, it says that the gradient structure that you have at the level of the particles and the weight induce another gradient structure for the flow at the level of the empirical measure, which is over the same energy, obviously, but with a specific metric. I'm going to tell you in a minute what this metric is, but there is something here that is already quite interesting that you can notice, is that since my loss was quadratic, right? What you have is that the loss was the L2 norm, weighted L2 norm of F and Fn, and since Fn, the function representation is itself linear in mu, this has now become quadratic in mu, plus a linear term here for the constraint. And so what does that mean in a nutshell? Well, this is a quadratic functional. So it has a unique minimum, okay, which is very different from what you would think at the level of the particles, right? We have simplified things. Okay. The reason why one needs to add these terms is that, unfortunately, you cannot guarantee that this minimum will be reached. There are more stationary points to this dynamics that they are minimal, and this term allows you to eliminate that problem by non-local transport. But I'll re-emphasize that in a minute. Okay, so now what does that allow to do? Well, it allows you to do, you can use all the apparatus that you have for particle system, interacting particle systems, which is the first one that you have at your disposal. It goes back to McKean, Vanden, etc., in a different context because they have noise in the equation. I don't have noise in the equation. Here, all the randomness comes from the initial data, or you draw the parameters, but it says essentially there is a mean field limit, which is that if you draw the initial parameters from some mu0 and the weights, I forgot to say about the weights, then this mu n, which is the empirical distribution that solves this equation, will converge weakly towards a mu that satisfies the same equation, except that the initial condition is different, which is that here you solve it with this initial condition. And so that means that if this measure here is sufficiently smooth, for example, it has a density, well, so will the solution of this equation. Okay, that's called the propagation of chaos, and that's a result that we obtain in this paper, and simultaneously, in fact, a little bit before, 2 weeks before, Andrea Montanari had posted a paper about that on the archive, and there was another group by Sirigano and Pilopoulos that posted something exactly the same day as us, making the same observation. Without this transport term, it was just the pure transport. Okay, so I have a little movie for those of you who are, don't know what the hydrodynamic limit is. The movie is a little bit misleading because it has nothing to do with neural network. It's just a system of interacting particles, but the movie is simply meant to show you why it's called hydrodynamic limit, and I think it will be fairly clear. Okay? So what the movie shows is this. This is a double well potential in which I put particles that feel this double well potential. That's the one particle interaction, if you wish. They all feel that individually. But then, so if there was only that, they would all fall back into one of the minimum there by gradient descent. But you do something else, which is that you put a bit of a repulsion between the particles. Okay? As a result, they don't want to be at the same place. In fact, if there was no background potential, they would just all fly to infinity. The actual dynamics is an interplay between they want to be low on this potential, but they want to be far away from one another. Okay? And I have just drawn them randomly from a Gaussian that's centered around that well. And then if you look at the dynamics, and you will see why it's called hydrodynamic limits, hopefully, this is what happens. So what you see here, and that's, if you wish, is what you're looking at here is that on the one hand, if you zoom on any given particles, is what the particles are doing. It's clearly not that interesting. What is interesting is what they do globally, right? What they do globally is the information that is embedded in the empirical distribution, which, as you can see from this illustration, should converge towards something which is fairly smooth, and that's the hydrodynamic limit. Okay? And so the movie, as I say, is not very relevant for machine learning, except for a few lessons that you can learn from it. In particular, don't think about what the particles or the parameter are doing individually. Don't think about what their landscape is. Think about the landscape over which the empirical or their probability distribution moves, because that's much simpler and much nicer. And instead of, looking into the detail into what's going on at the particle level, you can just focus on what's going on at this coarse grain level, where you just look at the distribution, which at the end will completely control the representation power of the neural network anyway. Okay? In particular, if you zoom closely here, you will notice it's just, for physicists in the audience, it's fairly clear what's happening. You're creating a crystal here, right, which is just triangular lattice. But since there is a mismatch between the shape it needs to take with the boundary, and also from the fact that this has just evolved randomly from an initial condition that was itself random, there are grain boundaries in it, right? So, if I were to think about the landscape from the viewpoint of the particle themselves, it's very, very rugged. Each time you start, you'd get something different. But if I redo the simulation at the level of the particles, and I just look at the empirical distribution, what you see is this, essentially. Okay? Okay, so What does that mean, right? Is that, so that's, that's illustrating this, right? And then, this transport that you have here, well, if you didn't put the additional weight, you would get the simple transport, which is essentially GD flow in Wasserstein metric. The way to think about that is the simplest, is if you take the GKO, Jordan-Kindler-Otto scheme, where essentially it's a proximal scheme, where the way you understand why the Wasserstein metric intervene is simply that it's a step where at every time you just minimize the energy, but saying that you need to remain sufficiently close from the previous value of the measure in Wasserstein metric. If you take tau going to 0, just with this line here, you would get this term in the equation. Okay? This term here is a change of metric, but you can also think about it in a two-step, which is you can think about it as that guy simply doing a proximal scheme, but where you replace Wasserstein by the KL divergence, by relative entropy. And if you do that, what you end up having is that, well, the combination of these two things as tau goes to 0 gives you that. There are mathematical papers where you can actually introduce, this is this Wasserstein-Fisher-Rao metric, where you can introduce a new metric that do these two steps into one. It's actually quite useful from a numerical perspective to think about this like that, because you can implement these dynamics at particle level quite easily. You don't need to, of course, we never work with the measure themselves. We always work with particles, so you can do that. Okay?
When Q goes to infinity or something like that?
Sorry?
Is that some limit when Q goes to infinity or something like that? Or what happened to Q?
Q is remain there as a parameter, which is simply, take 3 or 4, anything.
It doesn't enter into these equations?
It does, because it enters to the energy here, right?
Ah, okay.
This is the the energy is here, so it contains that guy. Yes? And in fact, that tells you why, if you think about this proximal scheme, it tells you why the norm of this function, right, the TV norm here, of this measure, cannot explode. Because it's controlled by this term, right? Lambda, we will see the role that lambda plays in a minute. Okay? In the original paper, we didn't have any regularization. We just looked at that. You can, of course, do that in that case, but then you don't control what's happening with the TV norm of the function. Okay. And so you can summarize what I've said so far into the following way, which is this. It says, suppose that you train, because again, we don't work with the measure themselves. So suppose that you train the network using, so you take your parameters, thetas, and the weights, and then you evolve them by stochastic gradient descent from well-prepared initial conditions. That just means you pick them initially randomly from something which is sufficiently smooth as a measure and independently, right? And then you do that by moving with stochastic gradient descent on the empirical loss, which is constructed over this target function f star. Then there are two results. The first one is that this guy, as n goes to infinity, has a limit, and this limit is nothing but the expectation of the units with respect to the measure that I showed you the limit on the previous slide. That's one. And that happened almost surely. That's a law of large number type result. And then you can write down an equation for this f of t. And since it's evolving on a quadratic landscape, and due to the unbalanced transport, you know that this guy will evolve to around a minimizer. And so you can actually show that, well, this guy will also have a limit in time with a certain f, which has the following two properties, and that's where the regularization is important. One is that its TV norm is smaller than the TV norm of the target, and how much smaller it is depends on how large lambda is. And if you look at the loss, so how far does this guy land from the target, this is controlled again by the TV norm and the lambda. So this just tells you take lambda sufficiently small to guarantee that you control things. Here lambda can be anything as long as it's there. There's a catch, which is that the smaller lambda, the longer the convergence time it takes here. But this convergence time here that you have there is independent of n. Right? That's because you have an algorithmic limit again. You are in the right scale. Okay? And so that's the first result that you obtain, which is to say, well, this is, if you wish, this is a dynamical UAT. It tells you that not only there is a universal approximation theorem, but in fact, if you do stochastic gradient descent on a network, and maybe you add these little tricks, which is regularizing a little bit the loss and using non-local transport via these weights, then you can realize it dynamically, which is that you will actually train to something which has a very small loss if lambda is small, and the TV norm is not so bad either. Okay, and these results were shown here. There were other results by Shiza and Bach that shows that in fact, if in certain cases you don't need the weights to have global convergence, and then there are other results by Shiza that also use some form of unbalanced transport. All of these results are without the regularization, so they cannot guarantee that this is true. In fact, they cannot guarantee. They need to assume that the dynamics has a limit, because it could be that the TV norm explodes. In this case, it cannot explode because of regularization. Okay. For people that do numerical analysis here, right, notice that it's a strange way to think about approximating function. Typically, when you do Galerkin truncation, you'd like to know what are your parameters in your Galerkin truncation. Here, you don't know what they are. Each time you train, you get different set of thetas, right? It's like you get something else, but it's just as good as in the other case. From a statistical perspective, it means that since the parameter can converge to many different values, it says simply that the model is not identifiable. Right? If you ask, I mean, have I identified the theta? No, you don't, because these are, again, they are quite complicated. Their landscape is the original landscape. Nothing has changed here. It's still as rugged as it was before. The only thing that we have gained is that we looked at the landscape of that guy, which is quadratic, and that's why it's simpler. Okay? But it doesn't matter, because that's what matters. Okay, now, I mean, once you have understood this, right, and see that, well, you ask, well, the next question, which is, okay, that's great, but what's the convergence rate in N, right? I mean, it could be that the convergence rate here is dramatically bad, and then it would be a problem. But you already know from one of the slides that I said before, that it should not be that bad, because if this is the law of large number, well, you have your next weapon, which is the CLT. So you just look at the CLT. So if you look at the CLT, what does it say? It says, well, you have the CLT with the usual scaling like this that says that at any finite time, if you look at the empirical measure and you subtract it from its target, you can multiply it by the square root of n, and this will converge towards a Gaussian measure. Okay? And these results are actually quite well known in the probability literature. I think the first paper about that, but I'm not completely sure, Gerard will know better, is a paper by Brown and Epp, and then there are many works by Snitzman and many others that have shown that. We just, right? Now, the fact that the measure here converge implies that if you test this measure against the unit, well, you get a CLT at the level of the functional representation. So whatever you can do at this level, translate immediately at this level. Okay? And then there's one thing that is perhaps not so trivial, which is that these are finite time results. But you can look at the equation for this Gaussian measure. In particular, it's a Gaussian measure with zero mean, so you just need to look at the evolution of its covariance. And then you can show that not only the covariance exists at all finite time, but that it has a limit as t goes to infinity. And so what does that mean? That means that the approximation error from the CLT, right, remains controlled on the same scale for all time, including at the limit t infinity when you have trained the network. This obviously is not a guarantee, and we can tweak the network in certain cases, pathological cases, such that it doesn't happen. For example, the covariance would explode. For example, if you eliminate completely transport and you just do only non-local transport, you would have typically divergence. But for the cases that I considered before, you don't. Okay? So you can summarize that in the following way, which is to say that, again, if you, same as before, you take this representation where these guys, the mu and the theta, are just trained by stochastic gradient descent over the empirical loss with regularization, then you can show that this limit exists, limit over n of n times the loss. This is the square, so that's the same as the square root of n over there. And then you can show that you can take the limit as t go to infinity and get something which is finite. Okay? And where this c, and that is important, is related to the TV norm of the target again. It's always the same. You're working always in the same space, so it's normal that it's always the same norm that appears. And so this C, I'm not giving you the expression explicitly. It's quite complicated because you need to solve an equation, but it is related to the TV norm of the target. Okay? And so this validates, the Monte Carlo bound to propagation of chaos at next order with a constant that's a priori known, because you can relate it to the unit and an equation that is satisfied for it. Okay? And these results were also shown here. The CLT was also for this type of setup proven in this paper by Sigano and Sibilopoulos, but they focused on the finite time result. It's really the infinite time result that is important if you want to know approximation error. Now, once you have done all this, how much am I doing? Or what am I doing with time? How much time do I have?
You have until 20 more minutes.
Oh, okay, so I should maybe slow.
Oh, no, sorry. 20 past, so 10 more minutes. But we are flexible, it's lunch afterwards.
Oh, okay. Sorry, maybe I can slow down a little bit then. Okay, so now there's another piece of the puzzle, which is the generalization error, right? Which is the question is, how good is the neural network if it's trained outside of the training set? Okay, and there, once you have established all the previous results, that one is almost a consequence of known result. In particular, there's a very nice discussion of that by Francis Back in a Journal of Machine Learning Research, a paper by 2017 that I already shown, where using tool from Radmacher complexity, it tells you the following thing. It says, if you look at the function, the best function that you can do, using the empirical loss, if you had infinitely many units, then if you use that guy and you evaluate it on the exact loss, so you try to interpolate outside of the data set, well then you get an error which is of this type. So there's a constant that goes like 1 over square root of p, and then there's again this TV norm, the regularization that you need to have that control everything. Now, the way I've stated the result here is in expectation, but if you have that guy, you can use concentration of measure inequality to actually do a little bit better than this and get probability estimate on what the probability will be.
I have a question.
Yeah.
How do these different terms depend on the input dimension?
Okay, so I'll get to that in a second. Bear with me. So first you have this says that there is no overfitting, but you need to remember that this, we have taken this guy here has been taken in specific limits, which is that this is what you have if you have infinitely many n, right? The number of units is infinite, and then you get this error estimate. But it suggests the following thing. It suggests that, again, if you have something which is, if you train your network by a stochastic gradient from well-prepared initial condition using the regularized loss and SGD, then you should expect that you will get an estimate of this type in the limit as n and p going to infinity. Okay? Where the first term here is the one that comes from the approximation error. The second term comes from the generalization error, and this is the little price that you need to pay, because in order to control the c's that are here, you need to control the TV norm of the function, and so you need to regularize the loss. Okay? The main difficulty, and why I'm not stating that as a proposition just yet, is that in order to do that, you need to go beyond the CLT, right? The difficult part is that guy, and you need to show that the CLT provides an estimate of the approximation at finite n. You want to change, in this result, you want to be able to interchange these limits, which is non-trivial. Okay, and that remains a bit of a sticky point, and I can discuss that offline later, right? That's what I've written here. Now, to go to your question, and I'll emphasize that at the end again. These constants here that I have not written are all given in terms of some complicated expression that depends on the TV norm that's there. The TV norm itself depends on the unit that you are using. And so one game that one can do, and that we are now trying to do, is that you can ask yourself, how does this C depend on the input dimension depending on what the unit is? Okay? And you can, for example, convince yourself very quickly that if you use radial basis function, for example, you want to say function on the sphere, and you want to represent it by Gaussian packets that you superpose. In that case, you can quickly show or convince yourself that this C will grow exponentially with dimension, the input dimension. So this, in some sense, breaks the curse of dimensionality, because the curse of dimensionality typically means that you have a C which is n to the, you would expect this, and we don't have that. We have something which is much better if D is bigger than, right? This is clearly better as soon as D is bigger than 2. But the C here on top of that depend on D and could be quite bad. However, and that might be an element of explanation as to why the ReLU are so good. If you do ReLU, then these guys depend on the dimension quite nicely. Intuitively, it's quite clear, because if you think about trying to represent a function with Gaussian on the sphere, right? If you want to have some approximation power, your Gaussian needs to be somewhat localized. If the Gaussian are localized, you will need an exponentially large number of them to pave the sphere in high dimension, right? It goes very badly with dimension. The ReLU, on the other hand, trying to understand how a ReLU is actually doing an approximation of function is much more complicated because they are precisely non-local. Each time, they essentially cut the sphere into two. But that also means that these constants are not so bad, because this problem of paving, you can pave the sphere with ReLU quite easily. One ReLU cuts it into two, another ReLU. So that's what. I'm not going to show you that, but these are the calculations that we are now trying to do. Okay. Right. So I have a few more minutes, so let me just discuss a few more topics. One is that we have only discussed so far, what I've discussed here is shallow network, or network with a very specific architecture. You can generalize all this if you look at networks that are deep with a specific network which is close to that of a convolutional neural network, where essentially what you do is that you construct a functional representation by essentially iterating on something. So what you do is that, from your target function here, what you do is that you start at x0 equal x, you pass it through one layer, and then you pass it again, then you pass it again, and you pass it again, and you take the kth output, capital K output, to be your functional representation here. Okay? Clearly, if you just look at this and you take n going to infinity, you realize that there will be a mean field representation of this result with measure, but it's just that you will have one measure per layer. So it complicates the analysis because instead of having one equation, now you're going to have k equations that are coupled k PDE for these measures, but in principle the analysis can be done just as well. Notice that in this case, however, the loss function is no longer convex even in these mu k, because if you take the square discrepancy between this f and the target, since you have all of this nonlinearity here, you have lost the convexity a priori at some point. Right? And so, but there is still the question, which is, well, maybe we can go to the whole program, and we are trying to do that, to show convergence if you use this unbalanced SGD with the weights, and to show what are the approximation and generalization error. A priori is this, the kind of the apparatus is the same. Use law of large number, use CLT, etc. So that we are trying to do that. Now, if I have a few more minutes, I want to make a link. This I will go fairly quickly because this is something that I think will be the whole topic of Andrea Montanari, and I don't know what he's going to talk about, so don't say that. Take what he will say and don't compare it to mine. But there has been something that has in the literature of deep neural network that has created quite a buzz, and this is a neurotangent kernel by Arthur Jacot and Clément Ongler. And Gabriel, actually, I don't remember his first name. And what they use is the following thing, is that you remember that there was this 1 over n, because I wanted to have, used the law of large number at this level, so I had 1 over n for the presentation. They say, well, what if you do 1 over square root of n? From a practical perspective, this is just changing the scale of the initialization, if you wish, okay? Now, clearly if you do that, right, your function here will not converge, and you want your function to converge. At least that to have a signal. What it will converge, if you just take that, is that to leading order, it will become a Gaussian field. The Gaussian field will not represent your target, so you need to go to next order. So if you use this scaling, this essentially says that you need to initialize the theta, the parameter, with a centric condition, which I write here if it holds strongly, but if it just holds in average is also true. Right? And then you need to go to next order. If you go to next order, what you end up having is that because of centric condition is that this guy here becomes again what you would get from the mean field scaling, which is 1 over n, but where you have, instead of having the phi, you have now the gradient of phi with this theta I 0 and something which is linear in front. Okay? That's the tangent condition in the neurotangent kernel. And so you can redo all the analysis at this level. And what happened is that this is much easier to analyze, because if you think about the theta, that in the training, these guys no longer evolve. The only thing that you're evolving are this discrepancy by a little bit. This guy remains centered in this way. And so what you end up having is essentially is a random kernel method. And random kernel methods are much simpler to analyze and to analyze the convergence property. In particular, you can write down an equation, which is the neurotangent kernel equation that they wrote, which is this one. in the mean field, you have a similar equation, which is this one. The only difference is that the kernel that you use, in one case, needs to be evaluated over the evolving measure. So this is a nonlinear equation, whereas in their case, it's given because it's fixed from the initial condition. And so, this is a linear equation. Again, it's a random kernel method. Okay, so this is nice. Because it says that training in NTK is much easier. However, there's a big price that you pay here, namely that if you do feature kernel, which is what you get, feature learning, which is what you get if you do training, as I explained for most of the talk, not in the Neuronal kernel, what you end up having is that you train in this space, space F1, which is of this function, the one that you can represent by a random measure in this way. If you do NTK, you're back into random kernel method. And if you're back into random kernel method, that means that you're also learning in a space, but this space is not this one. If you wish, it's the same space as before, but where the random measure that you are using needs to have a density with respect to the prior measure that you put on the parameters. That's always fixed. Okay? And as a result, with this condition that needs to be satisfied to be in the right space. And as a result, this space is much, much smaller than this one. And smaller space means bigger norm. And so that means that the approximation and generalization error that you have there are much higher a priori. Okay? Which is simply to say, well, something that people, I think, that work with machine learning know very well. It says that random kernel methods are completely beaten by feature learning, by machine learning, where you really use all the power of the network. You don't just do this linearization around the initial condition. That's the no free lunch conclusion here. Okay, and there are similar conclusions in this paper, and for some reason there was a reference to the paper of Andrea Montanari. I'm sorry, I don't. Maybe I put it somewhere. Okay, so anyway, that's the paper he will be talking about, I guess, in his talk. I'm out of time. I wanted to show you a test case where you can show that on a complicated function you can actually learn it with this neural network in ways which seems quite miraculous if you come more from standard approximation with Galerkin truncation, because it's a function in 25 dimensions where you just need hundreds of units and you can learn them, which is completely remarkable. But I don't have time to discuss that, except maybe just to show you that you can confirm the scaling of the error as 1 over n, even though you're in dimension 25. So it's clearly beating this with a constant that is not so bad, because otherwise I would not be able to, here I would get a number which is astronomical, and here I would get no signal. Right? These are the functional representation of the slice of this function. So it actually is working. And then you can also do something else, which is that you can indeed show that, and this I will have to skip a detailed explanation, but you can actually show that indeed the TV norm controls the generalization error. Meaning that if in the training, you track what is the TV norm of the function that you learn, and then you plot it, this is one of the curves here, and then you plot it against the generalization error, you see that they follow one another. And there is one curve here, which is the green one. This is the training loss, this is the test loss, and this is the total variation. The green curve is the one that you get by NTK, if you wish, where you see that it goes very well at the level of the training loss, but at the level of the test loss, it doesn't go well at all. And the reason is that it's not controlling very well the TV norm, which in all of the cases remain controlled, because that's what the feature learning, the one that I discussed most of the talk, is actually doing. Okay, so with this, let me just pass so a few concluding remarks, right? The first is that, what I've shown you here is that these theoretical results that support the empirical evidence, maybe when I say empirical evidence is too strong because there's more than empirical evidence, but that neural network can outperform standard interpolation method and massively reduce the cost of representing function in high dimensional space. Okay, it's a different perspective that explains within, using theory of probability and interactive particle system, why that's the case, right? what could be interesting, and that's related to the question of Lenka, is that it gives, in principle, a framework to understand how to carefully design this neural network, at least in the regime where I discussed them, because essentially because of this. Because if you go back to this main error estimate that is written a little bit colloquially here, the constants that are there, right, depends crucially on the loss that you use, the way you use the data, the unit that you use, and so on. Not that much about the training, but these facts. And so you, given an application, and I'm talking more to people that want to do scientific computing, you need to tailor your network and the way you use the data in the loss in such a way that these constants will depend gently on input dimension. I mean, if it's polynomial or something like that, that's more or less okay. If it's exponential, you're dead, right? There is evidence that in certain cases, like in the tau example that I showed you, that it's not so bad, which is remarkable, okay? And with that,